Hey, here's an example of a question that a student sent in about forces and Atwood machine and pulleys, and I wanted to just go through this with you guys just to make sure you understand how to do the free body diagram. These are the kinds of questions that I help answer my students. I create videos for them all the time. If you want to check out a little bit more about how I work with students, you can look in the description below, but I hope you enjoy it and find this helpful if you're struggling with forces at all. So we have a pulley, it's massless and frictionless, and we have these strings. They're inextensible. They're connected. So if a third object with mass of 26 kilograms is hung on one side of the 52 kilogram object is shown and the objects are released, the magnitude of the acceleration is most nearly. So the process that I always teach students to say when you're breaking down a problem like this is we're always going to do the first step is to draw the free body diagram of every object. And there was a previous lesson where I talked about how do we draw the free body diagrams. I would go take a look at that if you're not sure how to draw free body diagrams, but this is really useful for you guys. So let's do each of the blocks. So first is the 26 kilogram block. Okay, and the way we do drawing forces, we say, well, we always have gravity first, and that's equal to m times g, and it points downward towards the center of the earth. That's the rule for gravity. And then you think, what's touching the block? Okay, well, there's a rope here, so it's pulling up on here. And we'll call this T1, okay? And that's it. We're done with the free body diagram. Nothing else is touching the 26 kilogram block, so we're done. Now let's look at the left 52 kilogram block. Okay, so it has gravity acting on it, and because it's 52 kilograms, the gravity is 52g. Then you think, what's touching it? Well, it's got a rope down here, T1, and ropes always pull in the direction of the rope, so it's going to pull downwards, because ropes can only pull, they cannot push. And then there's another rope touching on top of here, we'll call this T2. Okay, now we assume that if the pulley is massless and frictionless, we're going to assume that the tension is the same throughout the rope. Okay, now if we have some mass, or if there's some friction of the pulley, or there's some mass in the pulley, then we have to start thinking about that. But the string is massless, so we don't have to worry about this. So that means we just assume that the tension is the same throughout the rope, if it's the same rope. These two tensions are different because it's a different rope. It doesn't mean that all ropes have the same tension, just that throughout the same rope has the same tension. Okay, the right 52 kilogram block. Now, this one has gravity. Mass is 52, so it's 52g acting downwards. And then it has T2 touching it, which pulls in the direction of the rope. Ropes can only pull in that direction. Okay, cool. After this, we would decompose any forces. If they're at angles, we would decompose into horizontal and vertical. These are all vertical forces, so we don't have to do that. Then the step after that, so usually 2 is to decompose forces. This is not applicable here. 3 is we want to identify the acceleration in the system. Now in this case, what's going to happen is this side's heavier, so it's going to accelerate downward. It's not actually important to get the acceleration correct, but just make it consistent. Know that for these two blocks, if we say they accelerate downward, and because the rope is not stretchable, it's going to move with the same acceleration, and this guy's going to move upwards with the acceleration. So they say this is down, this guy's going to accelerate downward, and this guy's going to accelerate upwards. And that's because they'll move in tandem together. When the left side goes down, the right side goes up with the same acceleration. Let's identify. You notice like I will use different numbers when I have to indicate that they're different values, but if it's the same acceleration, because the rope is not, it's inextensible, right? We assume that the rope, we cannot stretch it. If it were like a rubber band or like a bungee cord, then the acceleration might be different because it would be like they could move separately from each other. But this case, inextensible, like the rope is this fixed length, so one can't move faster than the other. Okay, so we've identified the acceleration, and now we're going to set the positive and negative directions. Now, it doesn't really matter what you do. My recommendation is to, for each free body diagram, always put the direction of the acceleration as positive. That would be my recommendation. Okay, so for each free body diagram, have that thing there. And that's because I always want to make the A positive. When you do kinematics, we do the same thing. We set the positive directions. And I always want to make A positive. So that's why I'm going to make down positive here. And then last, we're going to do F net equals ma. And now it's just a bunch of equations at this point. Now, you could obviously shortcut these steps sometimes, but I only usually do that if you're really, really good, like with a lot of experience. Otherwise, I actually suggest you do all of these. So let's look at the 26 kilogram block. F net always comes from your free body diagram. So if we say down is positive, any forces downward are going to be positive, like gravity, and any forces upward are negative, because we said down was positive. And that equals the mass of your free body diagram times the acceleration. For this guy here, we said down was positive, so it's going to be 52g is downward, T1 is downward, also positive, but T2 is upward, so it's negative. Equals 52 times, equals mass times acceleration, and acceleration downward, so it's positive. And for this guy, we said up was positive, so that T2 is positive, 52g is downward, so it's negative. And that equals 52 times a. Now, when you set it up this way, one thing is nice is you have a systems of equations, but if you add these all up, the minus T1, like add these three equations together, the minus T1 and plus T1 will cancel, and the minus T2 and plus T2 will cancel, and you can add these up. 26 plus 26, 52 minus 52 is 26g, and then this is 52, 104, I don't know, I'll just use a calculator, it's not a math class, 130a, and then if you use g of 10, g is 10, so that's 260, is equal to 130a, and so a is equal to 2 meters per second squared. All right, and so that's just a math problem at that point once you set up your equations and F net equals ma. So that's the same process I will use for any problem regarding that involve forces. I'm always going to draw that free body diagram there.